Okay, welcome to Section R.6 on radicals. All right, again, for some radical notation, if a is a real number and m is an integer and n is a positive integer and a to the 1/2 is a real, 1 over n is a real number. So if all of this holds true, then what do we know? Well, a to the 1 over nth power equals the nth root of a. And a times m over n equals the nth root of a raised to the mth power, or n root. Say that again. The nth root and a to the m power. Whew, that's a mouthful. Okay, so some absolute values. If n is an even positive integer, then the nth root of a to the nth power is going to be the absolute value of a. If n is a odd positive integer, then the nth root of a to the n is just a. So again, bear in mind that we are looking at the powers, the nth root, and what you're raising it to, and figuring out whether or not it's even or it's odd. And that lets you know if you're going to answer with absolute values or just whatever's on the inside by itself. So let's look at the first one. What do we have going on for a? So we have the cube root and something being raised to the third power. So those two match. So I can do one of these two options. Since n is odd, what can we do? Well, they can just cancel, and whatever's on the inside is left. So -3. For b, what do we have going on? Well, I don't really see a number by this radical, but whenever you don't see a number, you're allowed to assume that it's a 2. So we have a square root and a square. Okay, these are even, so we're working with this one right here, which means we need to take the absolute value. That's going to be the absolute value of -3. And what's the absolute value of -3? 3. Okay, all right, so moving on. What do we have here? Okay, so let's see. Now we have variables. So we don't actually know if our variable or the item on the inside is a positive or a negative. That brings in a little bit of trouble, but nothing too bad. So again, when we don't see a number, we're allowed to assume it's a 2. So we have the square root of x squared times y to the 4th. Well, to rewrite this so it kind of matches the form of one of these two, this is the square root of x times y squared to the 4th. Oops, sorry, I mean to the second power. Again, let's double check that. X times y squared squared, that would be, if I distribute the 2 in, x squared times y to the 4th. Okay, good, we didn't change anything. So now let's go ahead and simplify. And now, what's in the radical, the square root, is the same thing as being squared. So we can cancel, but careful, because in this case, n is a positive number, or a positive even number, it's a 2. When we cancel, we have to make sure to take the absolute value of what's on the inside. But we can't just drop the absolute values now because we don't actually know what x and y are. So we're going to go ahead and leave it with the absolute values. So depending on what x and y are, we know what to take. Now for the next one. At the moment, I just see that square root, and I don't really see anything square on the inside. I cannot simplify this way because we have that plus sign first, okay? So we can't just cancel like that. Be very careful. I need to have everything on the inside squared in order to cancel, not just one of the terms. So right now, only one of the terms is squared, which means I need to make the whole thing squared in order to use the property I'm trying to look at. But I think I realize this looks like a perfect square trinomial, which means it's going to factor 2, x plus 2 times x plus 2, square rooted, which is the same thing as x plus 2 squared. Aha, sneaky, huh? So now, again, we have that square root. So since it's a positive number, when we choose to cancel them out, we need to write it with an absolute value, x plus 2. And then there we are, we're done. So again, that was the trick. You have to be careful. You need to set it up so that everything in the radical is squared, not just one of the terms, okay? It needs to be the whole base squared in order to do this canceling thing. All right, so let's take a look at some rules for radicals. So if we have two radicals being multiplied together and they have the same nth root, we can go ahead and just multiply them together on the inside. Similar concept for these two. We have a fraction on the inside. We could split them up in between the two fractions, and nothing happens with the little radical piece. And then again, if we have a radical over a radical, it becomes that radical times this one together. All right, so some rules for simplifying radicals. No perfect squares should be underneath the radical sign. No fractions should be left under the radical. No radical in the denominator of a fraction. And then exponents in the radicand and index have no common factors. Okay, and again, what is the radicand? It is what is inside of the radical. Think of it as it's got cand, right? That is the radicand. And then what is in the index? The index is the little guy right there on the main part of the radical. So example 2, assume all variables represent non-negative real numbers. Okay, so before, again, on these two parts here, I didn't know if these were non-negative numbers, so I left the absolute values. But now, moving forward, I can assume that they're non-negative, so I don't really have to worry too much about those absolute values. Again, feel free to pause this video at any time to work on some of the problems by yourself, and then check in with me. So example 2, assume variables represent the non-negative real numbers. Let's see, what was I doing? Okay, yeah, so this is a square root. Now my goal is to see if I can create something squared inside of here. When I can do that, I can cancel them. Okay, again, and that's my goal. So I'm going to find a way to sort of finagle that to simplify. Well, 12 is not a perfect square, but is there a perfect square number within 12? There is, there's a 4. So I'm going to write this into my perfect value squared times the non-perfects. Again, I'm allowed to do that with our rules right here. So 12 can be split into 4 times 2, right? So I'll write the 4 here because it's a perfect square, and then the leftover 2 there. Again, this is my leftover box. So x squared, that is already a perfect square. We'll leave that here. Nothing goes in the leftover. And then y to the 6, is that a perfect square? It technically kind of is, because we can rewrite y to the 3rd power and square that. When we square that, that will become y to the 6th power. So I'll go ahead and leave that here, y to the 6th. Again, why am I doing this? My goal, again, is to get a perfect square inside of here. So something that can be perfectly squared so I can cancel with that radicand. Not with the radicand, with the index. All right, so let's see if what I have is correct. I'm going to go ahead and try to write it in that form I was talking about. Try to square it. So this is going to be the square root of, and 2 squared is 4. And then x squared would give me that x, and then y to the 3rd power would give me that y to the 6th. And then I'll write it, boop, with a square. Is that right? If I distributed in that 2, what would I get? I would get 4x squared y to the 6th. Good. That's what I had originally. And then again, the leftover was just that square root of 2, which I'll just write down by the side because we didn't get rid of it. It's just the leftover part. And now I can go ahead and simplify my radicals. And since we're allowed to assume everything is positive, we can just rewrite it without the absolute value sign, and then the square root of 2. And we're done. All right, let's take a look at the next one. This time, since it's a cube, our goal is going to be something, oops, that should be a 3, cubed. And when I get that, then I can cancel them. Again, that is my goal. Now, 27 is already a perfect cube number, so I don't really need to simplify that too much. So I can go ahead, I'm going to, again, write it in the numbers, or write the groups. So I have a cube root where everything's going to be perfect cube, times the cube root where my leftovers are going to go. 27 is already perfect, so I'll write that there. Now, n to the 6th. Would that be a perfect cube? It is. So we're going to go ahead and write m to the 6th down. How do I know it's a perfect cube? Well, because m to the 2nd power would give me m to the 6th. So that will be a perfect cube. Now, n squared. That one, I can't find a way to write that to the power of 3. So that's going to go in our leftovers box. or a leftovers radical. And then p to the fourth. Is that perfect? It's not, but I could split this into p cubed times p to the 1, and this is a perfect cube. So I'll put that one there, and this one's going to have to go to the leftovers box. Again, you're splitting it up between the ones that can be written into a perfect cube and the ones that are just the leftovers. So now I'm going to rewrite my first radical into something cubed on the inside so then I can show my canceling. Okay, so it's going to be 3m squared p cubed. Let's check to make sure the inside is correct. If I distribute that 3, I'll get 3 cubed, which is 27, m to the 6th, and p to the cube. Aha, yes, that is correct. All right, so we know we can go ahead and cancel those out. Oops, I forgot to bring down my imperfect one. And then I get 3m squared p times the cube root of n squared p. And we are done. Again, we can double check. Oops, this should extend long enough. I put the little tail there just so you can tell what's entirely in that radical. Again, the way to check if you're simplified. If the exponents on the inside are both smaller than the index. And in this case, we have a 2 and a 1. Those are all smaller than 3, so this one is as simplified as we can make it. All right, let's take a look at the next ones. Please take a moment and pause the video and see if you can try to simplify them yourself. But in general, this first one, again, my goal is to create something to the 4th power on the inside of this radical. And then all the values or terms that can't fit, we're going to put in a side one. So let's see, 16 is the same as 2 to the 4th power. And then we already have x to the 4th and y. How could we write y? We could do y to the 4th as well, and then what would the leftover be? So y to the 6th is equal to y to the 4th times y to the 2nd power. So the leftovers would be y to the 2nd power. That one went there, and that one went there. Again, we split the y to the 6th up into the perfect 4th root values and then the imperfect values. So rewriting this is the 4th root of, and again, I just like to rewrite everything so you can see that it's all to the 4th power times the 4th root of y squared. And that's going to be, well, let's see. Those cancel and they're left with 2xy. Now, when we look at the 4th root of y squared, remember, we can rewrite this as y squared to the 1/4, which is the same as 2xy times y to the 2/4. And those two can simplify. We had 1/2. So my answer would be 2xy times y to the 1/2 power. Ooh, and then we need to combine those two y's. So that would be 2 over 2 is the y. How did I get that? Well, let me do this in blue. Y to the 1 power equals the same as y to the... Well, how would I rewrite 1 with a base of 2? I could do 2 over 2, and that's how we get that. And then, how do you add fractions? 2 plus 1. So that's going to be 2xy to the 3/2 power. Again, there usually are a few different methods on how to do this. If you have any questions on your method, feel free to send a picture of your work. Send it to me via my email, and I'll let you know. Okay, so let's take a look at this next one. We're going to simplify. Ooh, I have a radical in a radical, and that makes me think of this rule right here. So let's go ahead and apply that. We'll multiply the two different indexes together. So that's going to be 3 times 4 root of 5, which is going to be 12 root 5. And we can't actually simplify that. So we are done. Alrighty, continuing on. Ooh, this is new. So now we have actual addition and subtraction between 3 different terms, and we need to simplify these terms. And if we simplify them, hopefully some of them will be like terms, and then we can add them or subtract them. So square root of 32, let's see. I'm going to try again and split these into a perfect and imperfect radical. 32 is the same as 16 times 2. So I'll break that up into square root of 16 times the square root of 2. Why did I do that? Well, again, the square root of 16 would be 4, so it splits perfectly. Then we'll bring down that minus sign. And again, 8 can split into 4 times 2. So the 4 times 2. And then plus, and this last one we can't simplify. That root 2 again is not simplifiable. So the square root of 16 is 4 times the square root of 2, minus the square root of 4 is 2 times the square root of 2, plus 10 root 2. And notice these are all like terms. They all have a root 2. So we have 4 minus 2 plus 10. What is 4 minus 2? That's 2. And then plus 10 more, that's going to be 12. So 12 root 2 is our answer. Now the next one. Again, our goal is to split it into perfect and imperfect. So 18. 18 is 9 times 2, and 9 is a perfect square. So we'll go ahead and write that in. The 9 is going to go in the perfect, and the 2 is going to go in the imperfect. So 9 times, and then the 2. Well, for the x, that's not a perfect square, so I'm going to go ahead and plop it with the 2. And the y cubed. Well, the y cubed is not perfect, but again, we can rewrite that as y squared times y to the 1. That will go with my perfects. And this one will go with the leftovers. See if you can split the last one. Okay, so hopefully you paused the video and tried this out by yourself. But we have plus, and then the y, we're not doing anything in the y yet, but let's see, 50. 50 is 25 times 2, so the 25 is a perfect square. And then that 2 is going to be left over again. And then the x, y's, those are both not perfect, so those will go with a 2. Okay. So, again, I like to rewrite things with the square if possible. I didn't do it in the last one, but let's do it with this one. This is 3y squared times the square root of 2xy plus y times the square root of 5 squared times the square root of 2xy. Okay, again, that rule for canceling applies. And we have 3y times the square root of 2xy plus, the 5 and the y we can multiply. So it's going to be 5y times the square root of 2xy. And do we have like terms? We do. This is 3y squared of 2xy's, and that is 5y squared of 2xy's. So 3 plus 5 is going to give me, how many? 8y square root of 2xy's. And again, make sure your radicals extend all the way. And there we go. All right, let's take a look at G. What is going on with this one? Well, we have multiplication going on between quite a few different things. So actually, I usually like to change the square roots or any of the radicals into fractional exponents. So the square root of x is going to be x to the half power, and I'm going to drop the parentheses and write everything out with the multiplication. And the fourth root of x is going to be x to the fourth power. Okay, so now let's go ahead and combine terms if we can. The 2 times the 3 is going to be 6. And then we can keep the base for x, and we can add the exponents. So that's an x and then a half plus a fourth. So in order to add these, we've got to create a common denominator with the fractions. So I'll do the building up property, multiplying everything by 2. And then we have 6 x to the 2/4 plus a fourth, which means we'll have 6x to the 3/4 power. All right, we're done. Now let's take a look at h. Let's take a look at h. What do we have here? We have multiplication going on between two different binomials. We can't add anything on the inside, so we're going to go ahead and FOIL. Remember, FOIL is when you multiply out the first two terms, so that'll be the square root of y times the square root of y, plus, and then you multiply out first outside terms, so it'll be the square root of x times, the square root of y times the square root of 2, and then you're going to multiply the that was outside, so inside terms for the I in FOIL, so that'll be square root of 2 times the square root of y. And then lastly, you'll do the last two terms of the L FOIL. So that will be square root of 2 times the square root of 2. Now again, there are different ways to approach this, so I'll show you the different ways that you can. So for the first two, we have the square root of y times the square root of y, which means, using the properties, we can multiply what's inside. That'll be the square root of y squared. Plus, now the square root of y times the square root of 2, I'll go ahead and use that same method, square root of 2y. And then plus for that other one, I'll go ahead and do the same, square root of 2y. Now for the last one, I'll show you the slightly different method you could do. You could change it to the fractional exponents, that's 2 to the half times 2 to the half. Now for this last one, the square root will cancel there, so we're left with just a y. Plus, and ooh, these two are like terms, which means we have 2 square root of 2y. Plus, and now lastly for these two, we can keep the base, which is the 2, and add the exponents. So a half plus a half is going to be 2 over 2. Can we simplify? Well, we can still simplify this. So that'll be y plus 2 square root of 2y plus 2 to the first power. And we're done. Again, try to be careful and make sure your radicals extend the whole way along. I'm dropping them a little bit, but it's best to make sure they extend the whole way so you know exactly what's under the radical. Now let's go ahead and do the last one. Feel free to try it yourself, but first off, I want to mention something. Notice in these two binomials that are being multiplied together, the first term of each binomial is the same. The last term is also the same, but what is different? There's a plus and a minus. These two are actually considered differences of squares. They're conjugates. So easy way to do this, instead of having to do all of the FOIL, we'll know that you can just square the first term, do a minus sign, and square the last term. Again, this comes from difference of squares, so you have x squared minus y squared is the same as x minus y times x plus y. Just a shortcut. If you did do the whole FOIL, you would end up with the right answer anyways. Okay, that's nice though, because that really shortcuts things. Go ahead, cancel out those squares, and we're left with y minus 2. Voila, done. Yay, okay. Ooh, we're getting close to the end of R.6. Rationalizing denominators. Okay, so denominators, again, are the bottom part of the fraction. What is rationalizing? Well, pretty much it has to do with getting rid of a radical from the denominator. You're not allowed to leave a radical in the denominator. It's considered not simple. So let's go ahead and practice some different methods for that. Again, simplify, assume all variables represent positive real numbers. So for this one right here, what's going on? We have a fraction in a radical, which we're not allowed to have. So let's go ahead and simplify that. The square root of 2 over square root of 7. But we still have a square root of 7 in the denominator. How can we get rid of that? Well, again, one of the main tools we have for expressions is the building up property. So the question is, could I multiply something to the denominator that could get rid of that radical? Again, think back to what we've been doing. If we had something squared underneath that radical, what would happen? I would cancel, and we wouldn't have a radical anymore. Wouldn't that be awesome? So the question is, what can I multiply to the square root of 7 that would create something squared? Well, if I multiplied it by the square root of 7, what would I get? I would end up with the square root of 7 times 7, square root of 7 squared. And then they would cancel. Okay, so awesome. That is great. That's what we're going to do. That's my plan, create something squared. But again, we have to do the building up property, which means if I multiply something at the bottom, I've got to multiply it to the top as well. So in the top, we'll have the square root of 7 times 2 is 14. And then square root of 14 all over 7. Alrighty, and we're done. There's no more radical in the bottom. Okay, let's look at the second one, part B. Well, this one's definitely more complicated. We have a 2 and an x squared, and this is a cube root. But our goal doesn't change too much. This time, because it's a cube root, we want something cubed underneath so that they can cancel. So again, that's my goal. I want a denominator with something cubed. So the question is, what do I multiply to the cube root of 2x squared in order to get some base amount cubed? So at the moment, that's 2 to the 1 power. If I multiplied it by 2 squared, that would give me the 2 cubed, right? And then if I multiply x squared by x to the 1 power, that would give me the x cubed. Okay, good, awesome. Let me just double check that. So I would get 2 cubed x cubed in the denominator if I did that. Yes, okay. Again, we have to multiply it to the top as well because that's the building up property. And we are left with 2 cube root of 4x to the first on the top. And then in the denominator, we have 4x divided by 3. And I'm going to simplify this on the inside so you can see what's happening. 2x to the third power. Those will cancel out, and I'm left with 2 cube root of 4x divided by 2x. Am I done? Not quite. We still got to cancel those 2's. We can simplify. Again, always simplify. Now we run out of room, so we're going to go ahead and draw a little arrow to show where we went. And we're left with the cube root of 4x divided by x. And we are done. Again, if you ever want a different explanation or to check your work, just send me an email, either with your work as a picture, or we'll set up time to talk about it in an office hour. Okay, these ones are a little different this time. They are now binomials. So in this one we have a minus sign in the bottom, and the other one we have a plus sign. So our tactic is going to change a little bit. We can't just straight up multiply it by another radical because it wouldn't get rid of the square root. I'll show you for example. If I decided to just multiply this by square root of 2, in the denominator I would have 3 root 2 minus the square root of 4, which would be 1 over 3 root 2 minus 2. So we got rid of one radical on this side, but then we have a new one. So that's not going to work. We have to have a new plan. And that plan is going to be, you're going to multiply it by the conjugate. What is that? Well, if you recall when we did the difference of squares, I called these two guys conjugates here because the only difference between these two terms is the sign. So you're going to multiply whatever this is by the conjugate, or the opposite version. So the opposite of this would be the plus version. And why do we care about that? Well, because when we do that, we end up squaring the terms. And when we square them, that can get rid of our radical. So that's our plan. Again, we're trying to get rid of the radical because we're trying to rationalize the denominators. So what's the conjugate of 3 minus the square root of 2? It's 3 plus the square root of 2. But careful, we have to do that to the top as well, because again, we're using the building up property. Yay! Okay, so in the top, 1 times anything is just itself, so I'll just write that out. Divided by, and again, we're using the difference of squares. So we'll square the first term, minus, and then square the last term. That's what this becomes. And again, that plan means, or hopefully, we should get rid of radicals. And indeed we do, those cancel. And we're left with 9 minus 2, which is 3 plus 2 divided by 9 minus 2 is 7. And we got rid of the radicals on the bottom. We're done. Good job. Give yourself a pat on the back. Again, as I have mentioned before, please make sure your equal signs line up. And if for some reason you can't work in enough room, use that little arrowhead to let us know where you're going. Okay, one more to go, and I believe, yep, we're done. Okay, again, pause the video, try this out by yourself, and check in with me. All right, so hopefully you try this by yourself, but again, the plan is to use a conjugate because we have a little binomial. So the opposite of the plus sign this time is going to be using a minus sign. So the conjugate of this one will be the square root of x minus 2 root 5. Again, we have to multiply that to the top as well because we're using the building up property with an expression. And in the top, we have the square root of x minus 2 root 5 all over. And again, because these two are conjugates, we'll just square the first term, which is the root x. And then we'll square the last term, which is the 2 root 5. Okay, in the top, we'll just go ahead and write that without the parentheses. Let's see, those cancel. Oh, careful for this one. We have to distribute that 2. So the 2 will cancel for the root 5, and then it'll also square the 2. So let me write that out with a few more steps so you can see what's going on. That's going to be 2 squared times root 5 squared. So root x minus 2 root 5 all over. X minus 4 times, and now those cancel, and we're left with 5. But it's still multiplication. So we have to multiply that out as well. And we get x minus 20. And we can't simplify that. Nothing else to simplify. The radicals are gone from the denominator, which again is what we were trying to do. So that's it. We're done. Alrighty, again, if you have any other questions about these lecture videos, if you want me to re-explain something in a different way, just send me an email and we can either make an office hour or we'll just explain it via email.